Syzygy, episode 90, Touching the Sun. And welcome back to another edition of the Syzygy podcast, quite possibly the final Syzygy podcast for the year 2021, which is exciting and weird and time's just doing very strange stuff. Joining me, not across the table in her office, as we've grown accustomed to once again, but across the other side of the country, Emily Brunsden. Emily, where are you? What's going on?
Yeah, so I've winged myself across the Pennines. I mean, by winged, I mean there were four wheels involved in the M62, of course.
Yeah, you didn't fly across, you just drove, which is the much more sensible way to do it in these times of COVIDness. Yeah.
So we are all just working from home, as the good Omicron variant tells us we should do.
Indeed. It does feel a little bit sort of deja vu-esque, doesn't it, to this time last year? But let's not talk about that. Let's not dwell on that. There's so many other cool things, particularly as, we're getting really excited here in Syzygy HQ for the launch of a certain space telescope. Emily, this was supposed to happen on my birthday. I was promised a birthday present a couple of days ago on the 18th that the James Webb Space Telescope, or the Just Wonderful Space Telescope, depending on who you ask, was supposed to launch. And that didn't happen. Why? What's going on?
Well, I think it just needed another 5 more minutes in bed.
Just needed to sort of, have a little bit more of a stretch, maybe another cup of tea. Yeah, look, it was delayed from the 18th to the 22nd. And then, hang on, we've got it up in the spacecrafty bit, but we just need to make sure that this bit's working okay. And look, you know what? With something like the JWST, I'm fine with them taking just a bit more time to get it absolutely 100% right, because we want this one to go well, right?
Absolutely. It feels a bit like a fractal pattern, doesn't it? That we're used to having delays that were like 2 years, 18 months, 6 months, and now we're down to 2 days, 3 hours,
Is this like a weird version of Zeno's paradox where, the time between delays is going to get shorter and shorter and shorter, but it's either going to be an infinite amount of time or will add up to a finite amount of time. And I really hope it's the latter and not the former. I hope that this is a convergent series of delays. So fingers crossed. It's supposed to be, I think it's somewhere around midday or just after midday UK time on Christmas Eve, the 24th of December. Tune in and watch this spacecraft take off with a really important telescope. Just remind us very briefly, Emily, why are we so excited about this telescope?
Well, I mean, it's only kind of like the biggest telescope we've ever launched since Hubble, pretty much,
Like biggest in concept and biggest in actual physical size as well?
Yeah, absolutely. Well, at least for optical telescopes. Actually, even our infrared telescopes haven't gotten this big. So yeah, we're talking about biggest in terms of the mirror size, but hugely biggest in terms of the science expectations of what we're going to be able to do with this instrument.
Yeah, it's going to be huge, but it also, bigger also means more things can go wrong. Like there's a lot that could happen here, and everyone's been working really, really hard to make sure that this one goes to plan. Fingers crossed. If everyone listening could just keep everything crossed just for the next few days, and then maybe a bit after that, after the launch, to make sure everything goes okay. And with any luck, in 2022, we'll actually get a bit of good news that it's all tickety-boo, everything's working as normal, and we have a new space telescope which is able to show us some awesome stuff. So come on, JWST, give us all the Christmas present that we in the astro nerd community so desperately desire. Fingers crossed. But look, that's not what we're here to talk about today. Today, we're talking about a different kind of space probe, one which you've probably seen a few headlines over the last couple of weeks, which is the Parker space probe. I've got that right, haven't I, Emily? It is Parker. And it's done something really kind of cool, which is it's touched the sun. What? Emily, what's going on? What are we talking about today? What's happened? And I guess we should probably also sort out fact from fiction. What hasn't happened? Have we actually touched the sun, Emily?
Well, it depends on your definition of sun. And you knew I was going to say that, didn't you? Because that's always where you want to start off
everything in astronomy has an asterisk next to it, right? Everything has a little asterisk that says, well, depends on how you define it. Yep. So how are we going to define the sun today? What's happened?
So we've had NASA's Parker Solar Probe, which was designed to go into the sun. Let's just make that clear. It's not an accident. We didn't just sort of
Yeah.
go a little bit off course and ended up in the sun. No, it is the solar probe, and it has actually confirmed that it has flown through the corona and sampled charged particles from the sun and its magnetic field as well.
Right. So we've gone for the first time, we've gone into and through some of the sun's corona. So we should probably have a bit of a discussion about that. What does that mean? But we've never done this before. We've never got this close to our sun, or indeed any other star. Emily, how are we going to unpack this? Should we start with, like, what have we gone through? What is the sun's corona? Like, how big is it? How close have we got? Take us through this. Give us something to hang on to here.
Well, I think we need to go all the way back to the very beginning to start with.
Okay.
And that is, of course, actually, what is the sun? It makes a good start, right? To an episode like this.
I think that's a really good place to start. I think we should start with that. Yep.
Right. So the sun is a sort of a ball of plasma. And a plasma is the fourth state of matter, as it's colloquially known, where you've got charged particles sort of swimming around in this sort of soup. And it's all held together by its own self-gravity. So that's what makes it into a sphere. Now, the sun has an inside and an outside. And this is sort of, in some ways, arbitrarily defined. But as we'll see, it's not a solid object because of this plasma. It's kind of got bits that are more dense and bits that are less dense. And there's physics that go behind that. But broadly, it is kind of this extended atmospheric thing.
Right. So it's not quite like the Earth in that you've got, like, there's clearly defined, this is the surface of the Earth. You know, this is the bit where it gets hard or wet, depending on where you are. But there's a fairly clearly defined surface there. We do have an atmosphere as well, but that's a lot thinner. And particularly the further away you go, the thinner it gets. But there's definitely a surface to the Earth. Can we say that there's a surface to the sun? Does that exist? Is that a thing?
We sort of do. What we call the surface of the sun is actually the photosphere. It's called the photosphere because photons come from the photosphere. So if you like, when you look at the sun, don't look at the sun.
Don't do that.
When you use a safe solar telescope or other viewing device to look at the sun, the surface that you're looking at is the photosphere. Okay.
And so when you see images of the sun, I mean, you look at a picture of the sun that NASA's taken or something, the Solar Observatory, and it really does look like that's a sphere, right? It does seem to have a really well-defined edge. So is that what you're talking about? That's the photosphere.
Yeah.
And so that really does seem like that's the edge of the sun right there. What's happening at that boundary to make it so well-defined?
So this is where the visible light that we see kind of, it becomes opaque to that visible light beyond that boundary. So the photosphere itself has a depth that's kind of something like 300 kilometers thick. So over that kind of 300 kilometers, which is tiny, obviously, compared to the whole size of the sun, then that's where all the photons are coming from, and we can't see past that with our visible light. Now, if you had X-ray sort of eyes, or if you had radio eyes or other types of eyes, then you would see a different surface because those photons hit a kind of you can't look any deeper, actually a lot sooner in both of those particular examples. So the sun actually looks a bit bigger in both radio and X-rays.
Right. So it depends on how you're looking. So unlike the surface of the Earth, where there is this sort of watery, rocky, dirty surface that is fairly well defined, the sun, it kind of depends on what wavelengths you're looking at as to where the surface seems to be. Is that right?
Yeah, exactly. But we take obviously the kind of natural thing, which is to take our own optical light as the standard, and this is where the photosphere comes from.
Yeah, because we're a bit biased that way.
Yeah. Well, it's in some ways it's the deepest layer that we can see to as well. So it's useful, and there's a lot of interesting things that happen in the photosphere. This is where our sunspots are formed, for example, that you see in lovely solar images. So it's a nice, useful example to take.
Okay. So that's kind of the edge of the sun as we see it. So, we've talked on podcasts before about what kind of happens down inside, but today we're sort of talking about what happens outside that. So, can we sort of move out from that surface? What's happening out there?
So then you have the solar atmosphere. So it's almost like we're pretending that inside the photosphere, the sun is like the inside of the Earth, and it's kind of there's interior composition, and that's fine, but we're kind of pretending that that's almost like a solid. That's the sun, and then outside of that is the sun's atmosphere, and that atmosphere is made up of 3 different parts. So we've got an order going outwards, and we'll go into the detail of these 3, but an order going outwards, we've got photosphere itself, then the chromosphere, then the corona.
So photosphere, chromosphere, and then the corona. Right. And so corona we're going to come back to because that's the meat of it today, because that's what the Parker Space Probe has actually been and touched, hung out in there for a while. So shall we work our way out then? Photosphere.
Yeah, so this is the surface we were talking about. So imagine that the surface is kind of the bottom of this photosphere, if you like. That's where the deepest photons that we see come from.
Right, but that's a layer you were saying. That's, what did you say, about 300 Ks thick or something?
Yeah. I sort of messed around with units when I was trying to figure out how we wanted to go here. In the end, I've gone with NASA's kind of way of describing things, which is to describe our distances in terms of the solar radius.
All right, let's work with that. I can imagine now a disk, that's the sun, and I've got a radius. That's one solar radius unit. Does that have a name, by the way? Like the astronomical unit is the average distance out to the Earth's orbit, and that's 1 AU, and we use that a lot. Does solar radius, is that a thing?
Yeah, well, it's a thing, and that we call it solar radius. We don't have a sort of fancy name like Martin for it, but we just call it solar radius.
Well, maybe we should. We'll call it Martins from now on. Okay. So given that we start at a radius of 1 Martin, 1 solar radius, what is the radius of the sun?
So it's about 700,000 kilometers.
So 300 kilometers as the thickness of the photosphere. That's not much.
It's less than 1%.
Right, that's fairly small. Yeah, okay.
So that photosphere is 300 kilometers thick, and we know this is what we call the surface temperature of the sun is somewhere around 5,700 Kelvin. Now I'm working in temperatures of Kelvin here. If you prefer degrees Celsius, then you can just kind of subtract off 243 degrees if you want.
Yeah, they're the same divisions, aren't they? It's the same size of a degree, whether you're talking Celsius or whether you're talking Kelvin. You just start in a different place. Kelvin starts at absolute 0, and Celsius starts at what we call 0, which is where water melts. But other than that, they're the same. And when you get up to sort of 5,700, look, it's hot by anyone's measure.
If you want to work in Fahrenheit, though, you're on your own here. I can't do that.
Yeah, no, you subtract your grandmother's age and divide by 9 and something. I can't remember. Yeah.
But so we're talking about 5,700 Kelvin is the temperature of the photosphere. So that was what we call broadly when we say the temperature of the sun. That's what we say the temperature of the sun is.
Okay, so we start from there, working our way out.
Yeah. Then we go out to the chromosphere. So the chromosphere is actually quite a thin layer as well. So, the photosphere is really thin. The chromosphere is only about 10 times thicker than that.
Okay, so where we were 300, we're now talking in the order of a few thousand kilometers thick?
Yeah, so up to maybe 5,000 at maximum.
Right, okay. And it's the chromosphere, and chroma means what? Color? What's happening in the chromosphere? Why is it called that?
Well, it's interesting. It's actually a really lovely red color. Now, the reason we don't tend to see this, so for example, if you are looking through solar viewing glasses or a solar telescope, is because it's much fainter compared to the rest of the photosphere. So the photosphere completely washes it out. The only time you can see the chromosphere is if you, for example, are lucky enough to see a total solar eclipse.
Yeah, you block out the really, really bright bit, and you can see the bit that's not so bright that normally gets swamped by all the light from the sun itself.
So if you look at some really nice total solar eclipse pictures, then you can see this really thin little red line, which is kind of going around the outside of the shadow of the moon. And that's our chromosphere.
So that's relatively thin. I mean, it's thicker than the photosphere, but still relatively thin. Okay, so you move out through that, and what's the composition of that? Like, what are we talking about when we're outside here? Is it still all the same stuff, just different densities? What's happening?
Yeah, it's all the same stuff. So it's kind of just more sun, so more
Right,
plasma, more charged particles,
more sun stuff.
mostly electrons, protons, a few kind of alpha nuclei, that kind of thing. But yeah, the density is going down, which is also why it's much less bright. So we're now down to something like 1/10,000th of the density of the photosphere.
So, and I'm assuming that the properties of the different parts as we move our way out from the photosphere to the chromosphere and then out to the corona, the properties of those are simply dependent on the density. It's a bit like the atmosphere on Earth, that you've got different properties for different parts of the atmosphere, just because things are getting thinner, and that means that different things can happen in different ways. The chemistry can be a little bit different. The the climate and the weather can be a bit different. And it's the same around the sun, I guess.
Yeah, exactly. Yeah, so the density is dropping basically as we move further and further away from the photosphere.
Okay, so photosphere, chromosphere, and then corona.
Corona. Yeah, so this is maybe something you will have seen or heard of at least. The corona of the sun is a much larger extended atmosphere of the sun. So it's got maybe we're not entirely sure, or at least we weren't until very recently, exactly how big the corona was.
Right.
Somewhere in the region of 10 to 20 times the radius of the sun.
Wow. Like
Guess.
that's big. That's really going out. And this is the one, like I've seen some pictures from eclipses. I haven't seen an actual eclipse myself. One day, Emily, one of our Patreon subscribers will pay for us to go to a solar eclipse. But I've never seen it, but I've seen pictures, and when the bright part of the sun is blocked out, I've never noticed the chromosphere, but you can't help but notice the incredibly large corona. It just goes on a really long way. But how far did you say? Like up to how many radii?
10 to 20 times the radius. So
Wow.
normally in those pictures, you can easily see that it's more than double the size of the sun, right?
Yeah.
But there's some lovely NASA imagery where you can kind of zoom out and you can see, and I think this is a coronal mass ejection video that comes from about 2012 when the sun was really active. And you can kind of keep zooming out and you can see this kind of little explosion come from the surface of the sun all the way out through the many, many layers of the corona, just taken with different observatories.
It's just amazing. It just goes on forever. So, and those images show that it's kind of got, like, there's a lot of structure there. This isn't just sort of, a simple spherical blanket around the sun. Like, there's a lot going on.
There is a really lot. Yeah, the first thing that I mentioned just then, without even rudely, not even explaining what I was talking about, was these coronal mass ejections.
Yeah. I mean, I was going to come back to that one.
Yeah, so these are ejections coming from the surface of the sun originally, but they're kind of like mini. No, they're not mini. They're really large explosions of
Nothing about the surface
particles.
of the sun is mini. You see some of these images or the videos where they sort of superimpose, this is the size of the Earth next to it, and it's just terrifying. It's like an image from hell. It's just amazing.
Yeah, so you get a big instability on the surface of the sun that can break, and then you get this enormous extra sort of ejection of charged particles that whooshes through the corona and then out into the kind of the final, I guess, what you might call layer of the sun, which is the solar wind.
So what can we just, before we leave that, what's going on there? I mean, you said a second ago it's sort of instabilities on the surface of the sun that then can make these sometimes small, sometimes enormous eruptions. But what's going on? Like, some of those are really big coronal mass ejections. Like, they're huge. So what can cause that?
Well, the biggest thing you need to remember about the sun, apart from the fact it's very large and very bright and you shouldn't look at it.
Yeah.
The
We'll repeat that
next
again.
thing
Don't
you
look
need
at the
to know
sun.
after those is that it's made of plasma, which means that you've got charged particles. Now, charged particles, if they move, generate a magnetic field. So they've got the actual movement of the charges itself is kind of an electric field, and then that induces a magnetic field. And everything to do with the sun is therefore part of physics, which is, I'm not going to lie, insanely hard part of physics, which is called magnetohydrodynamics.
So this is combining together fluid dynamics, magnetism, and presumably an enormous amount of sort of thermodynamics in there as well. Three of the hardest bits of physics that I remember from my degree individually, let alone when you combine them together to say, what the hell's going on the surface of a star? Can't be easy.
It's definitely not easy. These are none of my specialty subjects when I was at university. But then, of course, you've also got to add in a little bit of relativistic mechanics in there as well.
Oh, yeah. Just to make it fun, you know? Yeah. Why not?
So magnetohydrodynamics is tricky. It's really hard. But it's how we explain effectively all the activity that we see on the sun. So sunspots, for example, are parts of the sun where the magnetic field is such that the magnetic field of the sun is not like a lovely bar magnet like our own Earth's. It's just an absolute mess, actually, because of all these charged particles moving around all over the place. We've got differential rotation, which means that some parts of the sun rotate faster than the other parts.
That's going to mess things up. That's kind of tie all the magnetic bits together, which, like, magnetic field lines don't like that.
No,
they'll rebel after a while.
They bend and they cross and they break and they poke out of the sun at all sorts of weird and wonderful angles. So sunspots are an example of where the magnetic field is strong enough that you actually get a cooler region in the part of the sun that is the dark spot. Now, it's not much cooler than the rest of the photosphere, but it's enough that it looks like it's very dark compared to the rest of the bright photosphere.
Just a little bit cooler, not so much that it would make it a nice place to visit, but comparatively a bit cooler. So when we're talking about these big eruptions, is that an area where these magnetic field lines have just gone, no, this is just getting way too unstable and energetic. We've got to get out of here somehow. And they
so sometimes in the surface, you can get these what we call prominences, which are these big loops that can kind of pull out of the photosphere and go in a massive, massive arc. Now, these arcs can be several times the size of Earth, just one of these loops poking out of the sun. And that's a magnetic field line. And charged particles love to follow magnetic field lines.
That's what they do. So it's a magnetic field, but it's taking some of the sun's stuff with it on this little ride, which is kind of fun and big and energetic. But how does that then turn into we're getting out of here. This is a mass ejection. We're gone.
So many prominences are kind of quite, I guess, quiet, you might say, where the plasma just flows up off the surface of the sun, follows the loop and goes back down again into the surface. Fine. But sometimes these magnetic fields get very unstable and they break. So the magnetic field line's broken, which means you've now got this kind of plasma in a place that almost shouldn't be, in a sense. It should be on the surface of the sun, but it's now kind of pulled itself off in this magnetic field loop. It can break, and that then causes a huge eruption off the surface.
And these can be big. Sometimes they're really big, like the video you were talking about, which we'll put some images of and a link to in the show notes. But some are just frighteningly large, you know, when you consider how big the sun actually is. And then you look at this lick of flame coming off the surface of this thing and stretching out into space. That's terrifying. Like, does that just keep going off into space? It keeps
going, yeah. It's got enough velocity now for those charged particles to leave the surface of the sun, to leave the atmosphere of the sun, and to go all the way out into the rest of the solar system. And they are dangerous. I mean, let's not kid ourselves. The sun is dangerous.
Because, I mean, let's face it, we're going around the sun. I don't know if you know this, Emily, but we're quite nearby. And if one of those came in our direction, I'm guessing that wouldn't be great.
It wouldn't be great. Let's have a look at the solar wind, that bit that's going to carry these charged particles first, because that's the sort of medium through which these ejections are going to happen. So we mentioned we got up to the surface of the corona, right?
Yeah.
Now, the boundary between the corona, which is the edge of the sun's atmosphere, is actually got a very special name. It's called the Alphen's critical surface.
Presumably after someone Alphens who
discovered it? Yeah. He was very very prolific in understanding plasmas, magnetic fields. Plasma physicists, fusion physicists talk about them all the time as well. So,
right. And quite critical by the sound of it.
well, the surface is critical.
Right. Okay. It's not
It's
him
critical
himself.
because it's the edge. I guess it's another way you could say this is the edge of the sun. It's the edge of the atmosphere of the sun.
Okay.
And the reason why you can have an edge of the sun when you're talking about this kind of just nebulous sort of plasma thing is because this is the area, the region where gravity and the magnetic fields can no longer hold on to those charged particles that rest of the atmosphere. So that's the breaking point, if you like.
Okay, so that's our critical surface.
So this alpha critical surface defines then from corona to solar wind. So corona is held on to the sun, solar wind is we're leaving, we're off. The charged particles are off.
So the corona is still bound, even if it seems to be very sort of wafty and streaky and in all the images and stuff. It's still defined as bound. It's not going anywhere. This is still the outer levels of the sun's atmosphere, if you like. But you get beyond that and you're off. You're off into space.
Yeah. So if you give a charged particle enough velocity, just like anything, if you have enough velocity on the surface of the Earth and you jump, then you will leave the surface of the Earth. That's called the escape velocity of Earth. And it's the same for the sun. If you give your charged particles enough energy, they will leave the corona and they will go streaming off out into the rest of the solar system.
Cool. And that's solar wind.
Yeah. And that, I guess, doesn't really have a boundary in a sense. It's just kind of the constant flow of charged particles off the surface of the sun. It's going on forever. I mean, in a sense, because it's as far as those charged particles can go, maybe until the heliopause, and then you kind of start to define that's the edge of the sun's kind of magnetic influence on the rest of the galaxy.
Yeah, and that's way out there, right? That's way beyond like the planets and stuff. So by that point, it's a bit of a moot question as to whether or not you've truly that's gone. You're out there. You're in space now.
Yeah. So some of the best solar physicists that I've met, one of them was Lucy Green, actually, and she was talking about basically on Earth here, we do live inside the atmosphere of the sun. It's not the atmosphere as we've just defined it because we actually live in the solar wind, but nonetheless, this is a major influencer on the space around us.
So it's not just that we're influenced by the sun's gravity, although we definitely are. I mean, we're in orbit around it. But in that sense, like I'm thinking about the comparison to, say, the moon going around the Earth. The moon's not going through the Earth's atmosphere. The moon's not really affected much at all by the Earth's magnetic field, I guess. So the moon is going around the Earth just because of gravity. But the same's not true of the Earth going around the sun. That we have the gravity and that's causing our orbit and so on. But we're still very much influenced by the solar wind. We're within the sun in that sense.
Yeah, exactly. And then, it's significant. It's something like 1.5 million tons of sun per second are being ejected out into the solar wind.
That's a lot. That's a lot of sun. I mean, I know the sun's big, but that's a lot of sun.
Yeah, I mean, we don't have to worry in the sense of, in terms of the sun, it's only lost, I think it was 0.01% of its mass over its whole life through its solar wind.
Like, it's not going to dry up anytime soon. We don't have to worry about that. But it's still a lot. That I guess the point is it can have a big impact.
Yeah, so the solar wind would have a very profound effect on us. In fact, it would be very dangerous for us here on Earth if we didn't have the protection of our own magnetic field.
Right. And why is that? I mean, what's the danger?
Well, charged particles moving very quickly are not great for kind of living organisms.
You don't want that raining down upon you all the time. We get a lot of energy and light and heat from the sun as it is, but our magnetic field protects us from all the other stuff.
Yeah, so broadly, our magnetic field on Earth kind of, I guess it almost creates a little bubble around us where the majority of the solar wind gets deflected away from the Earth. There is a little bit that does come down into the atmosphere because it's funneled in by the Earth's own magnetic poles. And the beautiful, I guess, result of that is, of course, our aurorae that we get in the northern and southern hemispheres.
Right. Yes. Yeah. The northern lights and the southern lights. That's those charged particles funneling their way down through the magnetic fields towards the poles. What makes them glow? What makes them light up?
So they basically start bashing into particles in the atmosphere, mostly nitrogen and oxygen. And when they sort of bash into them, they give them lots of energy. To get rid of that energy, those molecules then release light.
So not only protecting us from all of that really scary stuff coming from the sun, but the magnetic field also gives us a really nice light show. And I'm assuming that means, I'm showing my ignorance here, I'm assuming that means that the aurorae, the northern and southern lights, they are much brighter and more interesting when the sun is going a bit nuts. Like when there's a lot of activity on the sun, we see that activity in the northern and southern lights.
Yeah. So if you ever want to travel to some of these lovely destinations and see the northern or southern lights, then you'll see that there's aurora forecasts. And these come from basically just watching the sun. Has it had any kind of little bursts of charged particles? And then 3 or 4 days later, those charged particles will arrive at Earth.
Yeah, I've signed up for one of those alerts here in the UK, and every once in a while I'll get there's an amber alert or a red alert or something like that. But it's always, so, if you live up in Scotland, you'll see it. Fantastic. I don't live in Scotland. I've yet to see. Have you ever seen the aurorae? Have you ever?
I'm a strange one. I've seen the southern lights, but not the northern lights.
Well, it's not so strange given the amount of time you've spent in New Zealand. That does kind of make sense. But did you actually have to travel to go and see it, or did it just sort of, you walked outside one day and went, oh, look at that?
So I was observing at the time. Actually, it's kind of unusual because in New Zealand, it's quite tricky to see the southern lights, much harder than it is to see them from the northern hemisphere.
Right. Why is that? Because you're quite far south.
Yeah, well, they tend to be, we're not that far south is the first problem. So where I'm observing, we're only kind of minus 40 something degrees south, which is, in New York, we're plus 50 something degrees, 56 degrees north. So we're not as far south as people tend to live north, if that makes sense.
Yeah.
And the magnetic South Pole's quite far away. So it depends on your distance. That's, of course, the distance to the geographic South Pole. You've got to worry about where the magnetic South Pole is. And then there's just an effect where they tend to be fainter, the southern lights.
Yeah, I always think with New Zealand, it's further south than it, and of course the very bottom of New Zealand is a very long way south. But New Zealand's quite long, and you can be in parts of New Zealand which aren't terribly far south at all. Yeah, fair enough. Okay, solar wind. We were talking about the solar wind, and we were talking a little bit about, can we just get back to the danger part? Because that's, the magnetic field is saving us at the moment from just common or garden variety solar wind, and that's fine. And without that, we'd be in trouble without the magnetic field. But that image of the really big, scary, sort of hellish solar flare, the really big coronal mass ejection, if one of those was pointed in our direction and we were just, in the path of that, would our magnetic field be able to cope with that? What kind of problems would we see there?
Well, yeah, I mean, the first thing you've got to worry about is all the things that aren't protected as much by our own magnetic field. So basically all the things that are above the atmosphere. So that's also, there's partly the magnetic field, but it's also the atmosphere itself, which is shielding us from the worst of these cosmic rays and the solar wind. So anything that's above, which includes the International Space Station, it includes the vast majority of all our satellites. These are much more vulnerable.
Communication satellites, yeah. And there's a lot of them up there, last count. It was quite a few.
Yeah, so the first thing that we need to worry about, of course, is our astronauts in space, because they are not particularly well shielded in the International Space Station. So, and there are protocols, the astronauts are trained on, okay, there's been a big coronal mass ejection. There's going to be all these charged particles arriving in, T-2 days. They will get everyone down off the International Space Station if it's really dangerous.
Right, like not actually just into the big padded room or something. They actually, no, we're coming to get you. You're coming home.
No, well, the problem is you'd need to have quite a lot of lead to stop these charged particles.
Yeah, fair enough. So I'm guessing that everything that is up there in orbit, has been designed for normal solar wind environment. They're being bombarded by charged particles all the time, but they've been designed for that. But they haven't been designed for these massive influxes of charged stuff. So every once in a while, yeah.
Yeah.
So if one of these big ones did come along, would it take out all of the communication satellites? Like,
Very easily. So in sort of, I guess not quite living memory, but in sort of slightly more than living memory, let's go a few generations ago, I think it was in the 1880s, there was an event called the Carrington event, which is probably the most famous, very large sort of solar storm that's impacted humanity. Because, before we had electricity, before we had Wi-Fi and 5G and whatever,
and satellites and all of that, yeah.
yeah, I mean, there wasn't anything electromagnetic to interfere with. So humans for a very long time were fairly oblivious to the fact that these solar storms could come along.
Yeah, I guess you're right. It's only in the last maximum 100 years that we would even conceive of being inconvenienced by the sun's activity. But now it would be a very big deal indeed. We've kind of made ourselves a little bit at the mercy of the whims of the sun now. That's a bit
Yeah.
worrying.
Well, you think about the 1880s, we didn't have a lot. We had telegraph wires. I think that was
Yeah.
like the main thing. But at the time, the reports were from this enormous solar storm that the operators of the telegraph wires would unplug their sort of equipment from the wire itself, but they could still communicate along the wire because there was enough electricity running along the telegraph wires just from the solar storm itself.
Wow, a
Keep
very early
going.
form of solar power. That's cool. Nice. Well, yeah, let's kind of hope that doesn't happen anytime soon. I mean, do these things happen often? Should we be worried?
Well, sort of. I mean, so I guess, and then coming to more living memory, there was a sort of a medium, small to medium electrical sort of discharge from the sun that came, I think it was in the 1980s. And it was Canada who took the brunt of this one.
Right.
And that took out loads of power stations in Canada because,
Wow. So
again,
it's enough to do that.
too much stuff going
wild.
through the system. Yeah.
That's amazing. Kind of makes you realize just how small and pathetically insignificant we are, really, isn't it? Just this could have happened. This could happen anytime. Do you get? I know we're going way off topic on this one, but do we get much of a warning of that kind of thing?
Well, if we do now, because we observe the sun very closely. We've got loads of telescopes pointed at the sun, some on Earth, some in sort of like SOHO and sort of trailing Earth orbits, SDO. There's lots of, we're watching the sun very closely, partially for these reasons, right?
You'd want to know.
And so you do get a warning in the sense it takes time for those charged particles to travel between the sun and us. So light only takes 8 minutes because it goes at the speed of light.
Yeah. Hence the name.
But charged particles take, a couple of days. I think it's about 3 days on average. So we got some time. What we could do about it, I don't really know.
Everyone take cover? Unplug? Yeah, hard to know. Well, look, let's get back onto the topic du jour, which is not coronal mass ejections. It's not the end of the world as we know it. It's that a very small but very cool spacecraft has done something really interesting, which is it's actually gone into the corona and hung out there for a while for the very first time. So, Emily, talk us through this one. What's the probe doing and what have we found?
Well, I think so far I've kind of presented most of the information as kind of just facts that we know about the sun, right?
Sure.
These are the different layers, these are the bits. Okay, we don't quite know exactly where the edge of the corona is, but Parker's about to tell us where that is, which is great. What I haven't really gone into is actually how much we don't know about all this stuff. And I want to share with you what I think is probably one of the most astonishing things in astrophysics, that we don't really know why it happens.
Do tell.
I mean, okay, we've got some other big contenders here. We've got dark energy, we've got black holes, we've got dark matter. But I think this is up there with you.
There are some big things, right? There's some big stuff we don't know. So you're putting this up there with, we don't know what a large quantity of the energy and matter in the universe is. That's pretty big. Not terribly certain about what goes on inside black holes, which is where physics breaks down. So that's pretty big. And you're putting this up there. So I want to know what's going on.
Well, so we mentioned the corona, this extended atmosphere of the sun. I deliberately didn't just, rattle off the temperature of this corona.
Right.
Remember, the surface of the sun is something like 5,700 Kelvin.
Yeah, give or take.
The corona is more than 1,000,000 Kelvin.
Wait, hang, what? How, that can't, no. Look, the sun, we all know this, Emily. The sun is the hot bit, right? That's the really hot bit. And then the further away you get from the sun, it's got to be the colder you get. Like that, nothing else makes sense. How can the corona, which goes on for ages, be like 1,000,000 Kelvin? That doesn't make any sense.
It makes almost no sense when you just sort of think, yeah, you're right. Your temperature should drop off as you go further and further away from
Yeah.
the sun. But instead, it gets something like 300 times hotter.
How? How does that work? That doesn't make any sense.
It doesn't make any sense. And the how is exactly the point. We don't really know.
Wow. So there's like, you're telling me we literally don't know. We've measured it and we know that it's true. We just don't know why.
Yeah, and this is the sun. It's right there.
Yeah. You can't, there's no others to go and measure. The sun's it. Like if we don't know about that one, what are we supposed to do? I guess that's the point, isn't it, of Parker? That's why Parker's in there, to try to give us
One
some
of the big
sense
reasons, yeah.
of what's going on in here.
Yeah, I mean, we do have some vague ideas about, that come from this magnetohydrodynamics, things like reconnection of magnetic field lines, which might sort of channel kind of extra energy into these sort of particles that are part of the corona, or even these alpha waves, which are kind of like little waves of these charged particles moving around on the magnetic field lines, which might kind of inject some energy into the corona. But I mean, the bottom line is we don't really know.
That's absolutely nuts. That absolutely blows my mind. So, I mean, I do know, obviously, that you can have very, very high temperatures in a very low density medium. And both of those things can be true. And that means that you don't actually have enormous amounts of energy. Like we tend to think that really high temperature means that anything that goes in, like there's nothing can survive at 1,000,000 degrees Kelvin, right? That's ridiculous. And yet, how can a probe go in there and hang out in there at 1,000,000 degrees? And it's because presumably the corona is really dispersed. Like the density's very, very low.
Yeah, exactly. Yeah. So it's very, very rarefied, which means that if you think about each individual particle, that what we define as temperature is kind of just basically directly related to how fast the particles are moving, right?
Yeah.
And they can move quite fast because there's just not that many of them. You don't need a lot of energy to make them move fast.
Right. It's still kind of surprising though. Like 1,000,000 seems a lot. So this probe, while it's not it's not like it's just done a deep dive through the photosphere into, the part of the sun that we see in those pictures. But I'm guessing it really had to be designed quite carefully to be able to cope with some pretty extreme environments.
Yeah, and this is one of the brilliant, I'm sure you've been able to look at some of the first images that have come from Parker from earlier this year. And some of those images show it moving into the corona and seeing all the particles just whooshing past.
Isn't that amazing? Yeah. There was a video that they put together from the images. And it really does look like it's just being blasted by high energy particles. But there was one other part of that video that I thought was really, really cool. Do you know what I'm going to talk about?
Oh, go on.
It's that as you're moving through, you can see all these what look like whizzing particles coming past, like these streaks. But then you can kind of see the stars in the background. And at one point, the Milky Way makes its way across the image. It's like, oh wow, like it just doesn't seem possible. It's the most magical moment. Yeah, very cool. I'll put a link to it in the show notes. But what an amazing thing. And it looks like such a terrifying environment. It's like something from a sci-fi movie. It doesn't look real.
So let's come back to Parker then. Let's focus on Parker, because Parker's done some amazing things and it's fairly short lifetime so far, right? It's only been up for a little while. So Parker is part of NASA's broader Living with a Star project.
Right, which we do, like that's not new, but
this is NASA paying attention. Living with a star wouldn't have been my choice of name. It sounds like a terrible disease, to be honest.
Name by committee there, I think. But okay, let's go with it. That's fine.
It is, here's some fun facts. It's the first NASA spacecraft to be named after a living person.
Okay. Who was or is, obviously, Parker?
Eugene Newman Parker is a solar sort of theorist looking at the solar corona and how some of this magnetohydrodynamics, how it all works. In 1958, published along with some other people some of his first ideas about how actually all this kind of corona comes together, and some ideas about why the temperature, for example, might be this stupidly high in the corona.
That's cool. So Parker's still kicking, still around, and gets to watch the satellite, the spacecraft that's named after, because it's not a satellite, it's a spacecraft named after him, going and doing its thing. That's never happened before.
Not for a NASA probe, no. Very cool.
That's cool. That's very cool. Go Parker.
So
Okay.
Parker launched in August 2018. Here's another cool thing. It only took until October 2018 for it to become the closest artificial object that we'd sent to the sun.
Wow. Okay, that says two things. One is it was really moving, and two, we haven't actually gone that close before. We've been to Mercury, right?
Yeah.
We've sent things to Mercury, and so presumably that's how long it took for it to get past Mercury.
Yeah, although it's on its first flyby. Remember that we don't just kind of point at the sun, launch, boom,
And then
there we
fall
go.
in. No, that's not the plan. It's going to be going around a few times, yeah?
Yeah. So lots of flybys of sort of Venus, the Earth, etc., to use all those gravitational energy to do this. But yeah, so if you're looking for scale, Mercury is at about 40% the distance of the sun as the Earth is,
Right.
which puts it at 83 solar radii.
And how far did you say the corona extends?
10 to 20.
10 to 20. Okay. So Mercury's still a long way outside of that. But it also gives you a sense of just how big that corona is. Like it goes maybe a quarter of the way out to the first planet. That's a lot.
Yeah. And this is where we actually come to, I guess, today's news story, which has been coming out, which is that it was in April this year, so April the 28th to be specific, 2021, it was then on this date that Parker actually crossed the Alphen critical surface and entered the corona for the first time.
So back in April.
Yeah. So it took a while to download the data and kind of figure it all out. So
I do love our habit on this podcast of like totally burying the lead. Like it's only taken us the best part of 40 minutes to actually get to what the story is. But that's okay. That's fine. We've had a really good chat along the way. So in April, so you said it was launched in 2018.
Yep.
And by October 2018, it was the closest thing we'd ever sent towards the sun. But it's taken since then for it to actually wing its way around a few times and plunge finally over that barrier into we are now in the corona.
Exactly. And so we can now say that we know that this Alphen critical surface is at 18.8 solar radii away from the sun.
Right. So pretty close to that 20. And would that be fairly uniform, or would that shift around a lot, or do we just not know?
Well, this is one of the interesting findings is actually it's not sort of a beautiful, nice, smooth sphere. And this is the extra surface of the sun.
Yeah.
Actually, it's this really wrinkled sort of surface. So actually Parker's been dipping in and out of it since then.
Right. Well, I mean, I guess that kind of makes sense when you think about the images that you do see of the corona, during an eclipse. It's not a big sphere around the sun. It's like got fingers out in all sorts of directions, and it looks really complicated. So it doesn't really surprise me that surface, the critical surface, would be similarly kind of all over the place.
Yeah, so it's really exciting to find that. And so this is actually adding sort of one more string in, I think, Parker's bow, because there's already been some wonderful discoveries that have come out, and it's the spacecraft's kind of 3 and a bit years. We've had, first of all, as it was working its way through the solar wind towards the corona, we had some really nice measurements of Alphen waves as it went through. And so we know that they do exist in the solar wind.
So that wasn't sure before.
Well, we thought they probably did, but at least we now know that they're probably very strongly linked to what's causing this corona to be intensely hot. So there's something to do with there.
Okay, so it's got that one. It's done that one well.
We also found that these switchbacks happen in the solar wind. Now, switchback is when the solar wind's kind of gushing out from the sun, but then just for a little bit, it pauses, goes backwards for a little while, and then goes back towards outwards again.
Why would it do that?
Well, it's just magnetic fields.
Who even knows? Who even knows what magnetic fields are doing? They're just ridiculous.
Yeah, these little zigzags. So that was quite exciting. And then just even earlier this year, it also found, well, you got these little switchbacks. They're happening much more often than originally predicted. And what Parker was able to do was trace them back. So imagine tracing that back through the solar wind, back through the corona, all the way back to the surface of the sun, and link them to these kind of funnel sort of shapes of energy released from the sun.
Wow. So it's not only been able to say these things are happening and we can see them, we can measure them. It's actually tracing their origins and their dynamics. That's so cool.
Yeah. So, it's doing really well.
Yeah, that's not bad. How long is the mission supposed to last?
I think it's a while. I've got the next I guess the biggest thing that people are looking forward to, in a sense, will be the closest approach.
Right.
So this is due to happen in 2025. And we're hoping that Parker will be able to get down to 8.9 solar radii.
Wow. So it's been out around the sort of 18 mark. That's where we've been. It's going to get like twice as close in, like half that distance. Wow. That's really close.
It's really close.
That's kind of scary. Could that be the end of Parker as we know it, or are we pretty confident it's going to be okay?
I think it should be okay, but I'm not an engineer, so I'm sure they've anticipated that it will get kind of a bit toasty.
Yeah, that is amazing though. What an amazing mission that we've never been this close before, and now we're really going to push it and just dive down, not quite into the sun, over the photosphere as such, but really getting in nice and close to almost be able to reach out and touch it. That's so cool.
And it's great that we can start to, well, at least kind of put together ideas about some of these embarrassing questions that we didn't know the answer to about the sun. Where does the atmosphere of the sun end? Not
we
really.
We don't know. What's going on in there? We don't know.
Why is the corona so hot?
We don't know. Tell you what, how about we make a spacecraft? Shall we do that? Okay, let's go.
So I think with all this kind of new information about the sun, it's obviously really, really exciting to learn the physics. We use the sun as our own test bed for understanding basically every other star that exists out there in the universe, because it's the one we can send space probes in to touch.
At least for now, it's the only one we've got. Yeah.
So it's very important for stellar physics as well as for solar physics. Of course, we want to understand all the activity on the sun because we do have a vested interest, being that it is kind of potentially quite disruptive, if not very dangerous, to life on Earth.
Yeah, it's a vested interest in the truest sense of the word, yeah.
So I think it's very exciting that we're able to do this. And I thought maybe I'll just leave you with this quote. And I take no responsibility for writing this quote. It was written by a NASA news journalist called Mara Johnson-Grow. This has been one major step for Parker Solar Probe and one giant leap for solar science.
Well, thank you, Emily, for a at times enlightening and at times quite scary view of what we know about the sun. I'm still blown away that we have no idea why the corona is like 1,000,000 degrees. That seems like the sort of thing that should be fairly quickly sorted out by the astronomers of the world. So I'm glad for your sake, for your profession's sake, that we've actually got the Parker Space Probe up there clearing that up for us. I think that'll help. That'll help you lot get your story together.
Yeah, I hope so.
Well, listen, you out there in Listenerland, if you have anything that you want to throw our way for the next round of Syzygy coming up in 2022, I can't believe I'm actually saying this. How is it possible that we're at the end of 2021? To me, it doesn't even feel like 2020. Anyway, 2022, if you want to get in touch with us and say, you should really do a story about this, or I've got a question, maybe we'll base an episode around that, or what's going on with this thing in the world of astronomy, then you can get in touch with us in a whole bunch of ways. Emily, name one.
So if you can get us on Twitter. Now, Twitter is a great place if you want to catch us at Syzygy Pod. That's SYZYGY Pod. But you're also going to need it for the JWST launch, as you are going to need all of the social media and all of the internet, because it is my plan on Christmas Eve to be sitting in my Christmas-themed pajamas, eating huge amounts of food, drinking lots of hot chocolate, and watching James Webb fly.
I think it's got to be done. I think that all of the social medias just fired up. This is one of the best things about social media, right? Social media is full of all sorts of nonsense, but what it does well is this kind of very exciting, and let's face it, very nerd-centric excitement about something like JWST launching. So tune in, it's going to be great fun. Watch this thing take off and keep our collective fingers and toes crossed for a successful launch. So at least we know what Emily and I are going to be doing on the 24th. And let's just hope for no more delays. I don't want any more delays. We need this one. So on Twitter, that's how you can find us. You can also find us on the Instagrams at SyzygyPod, same name. And we're on the Facebooks, if you're still doing the Facebook thing. Just search for us. Search for the Syzygy Podcast on Facebook and you'll find us. We also have a website, syzygy.fm, where you can find all of our past shows, all of the images that we've put up, the cool images, all of the links to all of the interesting stories that we've covered over the last several years of this podcast, as well as a contact page for you just to get on there and say hi and send us a little message and wish us happy Christmas. Speaking of wishing us happy Christmas, Emily, it's been a really good one. I'm looking forward to 2022. It's been a weird couple of years, I know, but I think 2022 is going to be big. I think 2022's got a lot of promise. I think there are going to be big, exciting things happening in 2022. What do you reckon?
Science is just going to rain down on us from the universe.
Yeah, I mean, in a good way, though. Not in a terrifying kind of end of the world kind of way.
Not in a coronal mass ejection kind of way.
We don't need any of that. We don't need that kind of thing. We need the good, positive, the science coming down upon us from the universe. So let's look forward to that. Emily, I'll see you in 2022. Have a great Christmas. Everyone out there in Listenerland, we'll catch you in the new year. Bye, everybody.
See you later.